As the final topic of this week, we are going to discuss the so-called object and box problems. And this has to do with the stars and bars representation. Essentially, we used it to count the ways to distribute indistinguishable objects, the stars, into distinguishable boxes, right? The order of the boxes was important because, well, if you remember the example, it was dish one, dish two, etc. If you swap them around, the order is different. So the boxes or the categories are distinguishable, but the objects, meaning the choices, are indistinguishable because the cook doesn't care which friend ordered which dish. So the objects are indistinguishable in that scenario. So we have seen how to solve this case. If the objects are distinguishable also, so the scenario is now distinguishable objects into distinguishable boxes or categories. This is now the multi-subset problem that we have already seen. For instance, how many ways are there to deal hands of 5 cards to 4 players out of a standard deck of 52? Now, essentially what you are doing is forming a partition, right? From 52, you would like to form a partition where you have 4 players, so you deal 5 cards to each of them, 5 to one, 5 to another, 5 to another, 5 to another, and the remainder, 32, is left out. So a partition in this format of 5 subsets, right? 4 of them has 5 elements and the other has 32. So this is how many ways? The answer to this is 52 factorial divided by 5 factorial, 5 factorial, 5 factorial, 5 factorial, and 32 factorial. Okay, so this we already also have seen earlier. Now the final two we haven't seen yet, and these in fact are quite difficult. The number of ways to distribute distinguishable objects into indistinguishable boxes. Now the boxes being indistinguishable usually complicates the problem. This we call is the number of distinct partitions of a set. Number of distinct partitions. Now here we had a partition here, but the format of the partition was fixed. Here, distinguishable objects, so the elements are different from each other. The elements of the set are distinguishable, but you distribute them into indistinguishable boxes. Okay, so this is the number of distinct partitions of a set. For instance, how many ways are there to distribute 4 different employees into 3 indistinguishable offices, right? If each of the offices can contain any number of employees, either 0 or 1 or 2 or 3 or 4. So you can put all of 4 into a single office and the other 3 can stay empty. Or you can put them one by one and add the remaining 1 into just one of them. Or you can put 2 in one office, another 2 in an office. Okay, so you have multiple alternatives. But now the offices are identical, they are indistinguishable, but the objects, meaning the employees, are distinguishable. For instance, if you put them 2 by 2, when you swap the employees, it's a different organization. So it's a different outcome. Okay, so you have to be careful about that also. The final one, the number of ways to distribute indistinguishable objects into indistinguishable boxes. Now this is the integer partitioning problem. How many ways to write an integer as the sum of positive integers? Okay, so let's see how we can solve this problem, because these two we have already solved earlier, and these final two are a little bit more complicated, and let's see what we can do about them. Now first, let's define the Stirling numbers of the second kind. And the first kind is not really that interesting, so we are just going to go into the second kind. This is the notation, or usually this one is much more widely used. This gives the number of ways to partition a set with n elements into R non-empty subsets. This is significant, non-empty subsets. So you are specifying the number of subsets here, but you are not specifying the number of elements in those subsets. If you remember the previous example here, in this example, the entire scenario was fixed. You have 5 subsets of this in this partition, and the number of elements are fixed, so you can just pick them out. But here, you have R non-empty sets, so you know the number of groups you have to form, but the number of elements in each subset is not specified. It's left free. Okay, it could have any element, any number of elements except 0, essentially. So R non-empty elements. Now, of course, by convention, 0 choose 0, 0 subset 0, let's say, is 1. So this is the number of partitions of the empty set where you just use 0 sets, 0 subsets. And of course, there is just a single partition of the empty set, so this is equal to 1 by convention. And clearly, n subset 1 is equal to 1. Why? What does this mean? This means you would like to partition a set of n elements into a single subset, which shouldn't be empty. Single subset means you have to put everything in that subset. So it's just one way. You can't do it in a second way. Similarly, n subset n. So this means you have a set of n elements, and you would like to come up with a partition with n subsets, which are not empty. Again, you have just one alternative here. You have to select, you have to place one element to each of the subsets. The order here is not important, because if you swap the subsets around, it's still the same partition. The order is not significant here. These are sets. But the elements are distinct. So still, this is equal to 1. So n subset 1 and n subset n are equal to 1. Okay, for n greater than or equal to 1. Also, n subset r should be 0 if n is less than r, because I cannot place n elements into r non-empty subsets where r is greater than n. So I don't have enough elements in this case. Okay, so this I'm going to come up with a recursive or inductive definition, and this will serve as my basis case. Okay, now how can I find a recurrence relation based on this definition? Suppose that a set of n elements to be partitioned into R subsets. N elements are subsets. Of course, the subsets should be non-empty. Do not forget this. Now consider one specific element out of n. Of course, there remains n minus 1 elements. When we consider that specific element, we can either use it by itself as a singleton, okay, or we can place it into one of the other subsets, which will not be a singleton. Okay, so in the first case, if we want to use it as a singleton, okay, the remaining n minus 1 elements should be partitioned into r minus 1 subsets, because one subset is going to be that singleton. Okay, so the remaining n minus 1 should be formed into partition of R minus 1 subsets, which are non-empty, which by our definition should be done in this many ways: n minus 1 subset R minus 1. So I'm selecting n minus 1 elements and forming partitions with R minus 1 non-empty subsets. And when I add the specific element I selected as a singleton, then I will have n elements and R non-empty subsets. Or case number 2, if the specific element is to be used in another subset, not as a singleton, but alongside other elements, then the remaining n minus 1 elements should be forming a partition with R subsets now, because with this specific selected element, I'm not going to form a new subset. It's not going to be a new subset. Therefore, the remainder n minus 1 should have formed already R subsets. And the number of ways to do that is this, n minus 1 subset R. Okay, then I'm going to choose one of them. There are R of them, right? R subsets. I need to select one of them to place this selected specific element into. So now I'm ready to write my recurrence relation. N subset R can be written as N1 subset R1. In this case, I'm using the element as a singleton. So from the remainder n minus 1 elements, I need to have R minus 1 subsets plus, so this is one way to do it. So I'm applying a sum rule here. The other way to do it is this, where I'm going to add this specific element into one of the R subsets that has been formed from the remaining n minus 1 elements, but I can also select R of each subset to put this specific element in. Okay, so along with this basis case, this gives us an inductive definition or a recursive definition of Stirling numbers of the second kind. And it's not quite straightforward, but we do have a closed form expression for this provided here. And remember what these give us: the number of ways to partition a set with n elements into R non-empty subsets. So using this, we can actually compute the total number of partitions a set can have. The partitions of a set with n elements, these are called the Bell numbers. Okay, and simply these are equal to the sum of all possible partitions where you have R subsets. So to partition a set of n elements, you can use one subset, two subsets, three subsets, four subsets, up to n subsets where you use all singletons. Well, R is included here for some other relationships to hold, but as you know, this will be already 0, so it's not going to spoil the addition. And finally, coming back to the question, the number of ways to distribute n distinguishable objects into R indistinguishable boxes is given by this sum, right? The Stirling numbers of the second kind, where you are forming partitions of size n or number of n elements using I subsets where I runs from 1 up to R. So in our example, it was 4 employees, if I remember correctly, and 3 rooms or 3 offices. So here you would like to form partitions of 4, n equals 4, and you can use 3 rooms, but the rooms can be empty. Okay, but at least one of them should be non-empty, so I from 1 up to 3. So I can use 1 room or 2 rooms or 3 rooms, and then I will have the partition 4 into I subsets. So I can either partition 4 into one subset, 4 into two subsets, or 4 into three subsets, and then add them up, and that will give me the desired result.